All right, we want to wrap up chapter 6 today. And the last component we need to discuss is intermolecular forces. So I'm going to bring in our video demonstration that you watched about the rate of evaporation of our three components. Okay, so let's talk about our components. And I put this graph up here from our demonstration. We'll probably go back to it. So the first thing I want to do is talk about things we already know. So for example, we should already know how to draw the Lewis structure for water. And we should know that water has an angular shape. And so these unshared pairs of electrons on oxygen pushes those hydrogens down at an angle. So that makes my water molecule polar. Rubbing alcohol. So here's the formula. It is C2H5OH. And it's written in this format because the carbons are all going to be bonded together. And these 5 hydrogens are bonded to those 2 carbons. So we can put 1, 2, 3, 4, 5. And then this oxygen gets bonded to a carbon. And then that hydrogen is bonded to that oxygen. So it looks like this. And so this oxygen end, again, pushes those atoms down at an angle. But these carbons do not have that same dipoles at an angle situation. So this molecule is only going to be slightly polar. And then we have butane. So butane is C4H10. So we would have carbon would be the central atom and there would be 4 of them. And then we need to finish out carbon having 4 bonds by bonding hydrogens to it to complete it. So this carbon already has 1, so it needs 3 more bonds. This carbon has 2 bonds, so it's going to need 2 more. This carbon has 2 bonds, so it's going to need 2 more. This carbon only has 1, so it's going to need 3. Okay, so there are my 10 hydrogens. Okay. And all of these are going to be pulling equally in all directions. So this molecule then, for that reason, is going to be nonpolar. Okay. So if we looked at the graphs, we saw that butane had the fastest rate of evaporation. Water had the slowest rate of evaporation. And we're just going to call rubbing alcohol, it's in between the two. So we'll say it has an intermediate. All right, now their rate of evaporation is based upon their intermolecular force. So IMF is the abbreviation for intermolecular force. So it's the force that's acting between the molecules. And so the reason why water has the slowest rate of evaporation is because it has the strongest intermolecular force. And the intermolecular force that water has is called hydrogen bonding. And you can look up hydrogen bonding definition, but the gist of this is that you have in a molecule, you have hydrogen that's bonded to a highly electronegative element. And if you're thinking about trends in the periodic table, the elements that are highly electronegative are in the upper right-hand corner. So I'm referring to hydrogen bonded to oxygen, or hydrogen bonded to nitrogen, or hydrogen bonded to fluorine. So here's what I have. If I would have to have two water molecules, so let me draw a second over here in my picture. And so my intermolecular force would be this. This hydrogen would be attracted to the oxygen of this water molecule. Because if you are thinking about polarity, remember that oxygen is highly electronegative. It has an electronegativity of 3.5, where hydrogen is only 2.1. And remember, this creates dipoles. And so the way we label dipoles is that the element that is more electronegative would have a partial negative charge, and the element that has the lower electronegativity would be partial positive. So we kind of get charged regions in this molecule. So this hydrogen that's partial positive and this oxygen that's partial negative are attracted to each other. All right, then let's talk about rubbing alcohol. So rubbing alcohol, you could say, has the second strongest intermolecular force. And the intermolecular force here is called dipole-dipole. And really the requirement here is that your molecule has to be polar. Which rubbing alcohol is slightly polar. So it's really important to stress the fact that you need to be able to draw Lewis structures true to their shape, and their shape affects their polarity, and their polarity affects their intermolecular force. So it's all tied in together. All right. The relationship here, because we know polarity can vary depending on how electronegative the elements are. What we typically see is the more polar the molecule, the stronger the bonds. And a really great indicator about strength of bonds that we looked at when we kind of started chapter 6 is by looking at things like melting point. So we see that these, if you have polar bonds, you typically have high melting points. All right, now, since butane evaporated the fastest, what this tells us, it has the weakest intermolecular force. And the intermolecular force it has is called London dispersion forces. Now, London dispersion forces are caused by the movement of electrons, and that movement of electrons causes temporary dipoles. So it's really important to note all molecules have electrons that are mobile. So in actuality, all molecules have London dispersion. So I'm going to go back up here, and in my water box, I'm going to put that this also has London dispersion forces. and that my rubbing alcohol also has London dispersion forces. But molecules that are nonpolar are the only ones that only have London dispersion forces. And what we typically see with London dispersion forces is that these LDF, that's the abbreviation for London dispersion forces, increase as the molecule gets bigger. And again, the way we can tell size is by the molar mass.